In this objective, we're looking at 1.2 mass spectroscopy of elements. So our learning objective is to explain the quantitative relationship between the mass spectrum of an element and the masses of the element's isotopes. So let's kind of recap and refresh ourselves on the three definitions from our basic chemistry class. So an atom is going to be our basic unit of a chemical element. Please note that the atom is going to be our smallest unit of matter. And so when we talk about elements from our periodic table, and before I talk about isotope and ion, generally when we look at a periodic table, we're talking about neutral elements, okay? So with neutral elements, they'll have the same number of electrons as the number of protons. Okay, because remember we have protons, neutrons, electrons, which I'll actually talk in the next part as well. But when it comes to protons, it's going to be a characteristic for an element. So the number of protons an element has will be a characteristic. And that comes to looking at the atomic number, so that number that's associated with each element. So for example, carbon has an atomic number of 6, so it has 6 protons. If you change those number of protons from 6 to 7, you don't have carbon anymore, you would have nitrogen. Okay, so an isotope is going to be 2 or more atoms with different masses. And remember, mass is going to be based off the number of protons plus the number of neutrons, okay? And then few things to just kind of talk about. So ion, when I was referencing neutral elements, here, this is, when it comes to an ion, this is an atom with a net charge, plus or minus, because of varied amounts of electrons compared to protons. Okay, so here, I know I didn't leave us too much room. We have two types of anions. We have two types of ions. We have an anion, which is negative. Here, we're going to have more electrons than protons. And then we have a cation, which a cation is positive. Here, we have less electrons than protons. Okay, those are two terminologies you'll need to know when it comes to those different ions. Please note with an ion, there is no change to the number of protons. The only thing that you're changing is electrons, okay? So changing number of, changing number of electrons. And then just to go back to isotopes, just kind of to remember, if we're talking about 2 or more atoms with different masses, these 2 atoms will have the same number of protons, just different number of neutrons, okay? And we'll talk more about that. All right, coming down to here with atomic structure. So, I've been kind of using kind of a shortened annotation. So electrons are going to be E with a superscript of negative. Protons are going to be P with a superscript of positive, and neutrons is N with a superscript of 0, indicating that they're neutral, okay? Remember, inside our nucleus of an atom, we'll have our protons and neutrons, and then outside of it will be our electrons, okay? You can kind of see by this chart right here, indicating where are these subatomic particles found. It then talks about charge. It then talks about mass, which is an AMU, which stands for atomic mass units. I'll have it on a later slide. And then how much that would be in mass of grams, okay? Here, don't worry so much about memorizing how to get it to grams. Those grams we would not be able to weigh on a normal balance. We wouldn't be able to get to that many decimal places. So just kind of indicating that they're very, very, very tiny, okay? All right, moving on. So Here, before we actually start like filling in this chart right here based off different isotopes, here I kind of want to show you a notation. All right, so this notation looks like this: X, A, Z, and C. So A right here is going to be our mass number. So remember, mass number is the number of protons plus the number of neutrons. Z right here is going to be the atomic number, which is going to be just the number of protons. And remember, number of protons will tell us what element that is, just looking at a periodic table. X right here is going to be our chemical symbol. Remember, a chemical symbol can either be one letter or two letters. If it's two letters, our first letter will be capitalized, the other one will not be. And then C right here, sometimes you won't see something in the top right-hand corner. If you do, this indicates, this will indicate charge. This is just charge of the atom. If nothing's there, we assume neutral. So if nothing's there, we assume neutral. Remember, that kind of goes back to what ions are, okay? All right, so let's look at this example right here. So I actually did the first column for us, okay? This is that isotopic notation that I just was showing you above. So here you can see K stands for potassium. 39 is going to be our mass number. 19 is going to be the atomic number. And this right here is indicating that it's charged. So here to fill this in, I put 39 for the mass number because that's what that told me right here. Atomic number is going to be this number right here. These two, atomic number and protons, will always be the same number. Neutrons, the only way to find neutrons is to take the mass number and subtract atomic number, and I'll write that off to the side right here. So here, to find neutrons, we'll do mass number minus number of protons, and that will get us number of neutrons. And then electrons, you can see that it is considered 18, all right? If this was a neutral element of potassium, protons and electrons would be the same. But because it has a +1 charge, we have lost electrons, okay? Sometimes I like to do the math plus 19 because those are 19 positive protons. And if I have 18 negative electrons, that gets me that +1 charge, which matches that right there. That's kind of a little trick you can do. All right, so let's try this example together. We have mercury 200. Sometimes you might see this type of notation where they give you the element name dash mass number. I'm actually going to write this up here. So here, this was called isotopic notation, which is just kind of like that one above us. This one is another type of notation where you get the element name dash mass number. So let's fill in the chart. So here, that 200 is my mass number, so I'm going to put 200 right here. They told us atomic number is 18, which should be the exact same as the one below, which is protons. Here, to figure out neutrons, we will do the 200 mass number minus 80 protons, which gets me 120 neutrons. To figure out electrons, they didn't say anything about it being an ion, so I'm going to assume that it's neutral. So here, since I have 80 protons, I'm going to assume I have 80 electrons. Positive 80 minus 80 equals 0, which is neutral. All right, why don't you pause the video and try these two yourself. Once you finish, press play and I'll go over the answers. All right, so let's go over the answers. So this one is another type of notation where you get chemical symbol and mass number. And then this one right here, you could also, this is just kind of looking at it just an ion by itself. So there isn't an actual name for this. It just looks like the ion, okay? I'll just put here that this is an ion. All right, so zirconium 92. So 92 is my mass number. I'm going to zoom out for this. Here, I I was told 40 protons, which will be the same as atomic number. To find neutrons, I'm going to take mass number minus protons, which gets me 52 neutrons. And then lastly, to figure out electrons, it didn't say anything about zirconium being charged, so I'm going to assume same number of electrons as protons, so 40. Next one, I have Cl minus 1. So they gave us the atomic number in protons of chlorine, which should be the same. Here, they didn't tell us anything about the mass. So in a situation like this, if they don't tell you like neutrons, or if they don't tell you anything about mass number, I would just look off the periodic table and either round that number up or down, okay? Because that's going to be, remember that number on the periodic table is an average of all the different isotopes for that element. Chlorine's 35.45. I'm going to round it down to 35. Then it comes down to neutrons, so 35 minus 17, I get 18. Now to figure out what the charge is for number of electrons, here we can't put 17 electrons because it is charged of that minus 1 right here, okay? So here, because it's charged, we have more electrons. So if I did plus 17 minus 18, I get negative 1. So here, I'm going to have 18 electrons. And again, this negative 1 is supposed to correspond to the charge of it, okay? All right, moving on. So on the periodic table, the mass of element is given as a relative average of all the elements' known isotopes, okay? And so this is referred to as the average atomic mass. And so that's kind of what I was saying about the chlorine example, that 35.45 is taking into consideration all of chlorine's isotopes, you know, and they all have different percent abundances. Some are higher than others, but since our average is around 35.45, it is safe to say that there's an isotope of 35. You will notice that in all of these problems, I was just using whole numbers because I'm counting. I'm counting that there's 35 protons plus neutrons, okay? And so here, you did not want to use the average value on the periodic table, okay? Few things that I want to talk about when it comes to average atomic mass. There are two different vocab words for us to know: percent abundance versus relative abundance. So here, when it comes to the percent abundance, this is going to be the amount present out of a sample. So when you think of a percent, hopefully you're thinking in your head 100%. So the relative abundance is connected to the percent, but here it's going to be the decimal form of the percent. So here you basically would take the percent and divide by 100 to get a decimal. Okay, we use the relative abundance for the math portion for this unit, okay? And I'm going to show you kind of an example of why we need to get relative abundance. So here, I'm going to give you like a quick scenario to show you what I mean by the math portion. So let's say you go out to lunch and your bill is $20 and you want to tip 20%. Well, here, you would not do 20 times 20% because that would be 400. This does not make sense at all. So here what you would do, sorry, I'm going to zoom in. Here you would take the $20 bill and multiply by 0.20, because here if you take 20% and divide by 100, you get 0.20. So here, this actually helps us with the math. Here, 20 times 0.2 gives us our $4 tip. So here, always take that percent out of 100 if you're going to be using math with that percent. All right, the next part of this lesson is talking about mass spectrometry. Mass spectrometry is also known as spectroscopy, which is just measuring the mass of atoms and molecules. And so it is a technique that separates particles according to their masses. And so it's actually a pretty cool device to use. It's very expensive, but basically you inject the spectrometer with a sample, and chemistry happens. And so there's stuff that happens on the atomic level. And in the end, this instrument is able to produce a graph that leads to me on the next page. It's able to give you a graph based off the amount they saw, and that amount that was present, it correlates to the percent abundance, but you'll get some peaks, and it will tell you actually the masses that they were able to detect based off that sample. So here, the position of each peak on the x-axis, like I said, is going to be based off mass. And again, when we talk about mass, it's protons plus neutrons. And then the height of the peak, which is the y-axis, it will be the intensity. So that's why I was saying the abundance, the amount that was there, okay? Now, please note that the total intensity must be normalized. So it must equal 100%. If it doesn't equal 100%, I can show you that in just a second, okay? But all you would have to do is divide the intensity of each peak by the total. So I'm going to zoom in right here. So let's say your total intensity was 150% and you had two peaks, one that was 100 and one that was 50, okay? So the way that you would fix this is you would take the intensity of each peak and divide by the total. So here we get new peaks and then times 100. You would get 66.67% for that peak. And then this one would be 33.33% for that peak. Total, you'll get your new one of 100% rather than 150. All right. So here, once we have 100%, you're actually able to calculate the average atomic mass if you're given a mass spectrometer graph. So here, I'm going to show you the equation. I'm going to use AAM, and that's for average atomic mass, just because it's a long word. So average atomic mass would be the mass of our first one, and our mass is either going to, most times it's going to be given in AMU, which AMU stands for atomic mass unit. So you'll take the mass of the first isotope, and again, mass is protons plus neutrons, and you would multiply by the relative abundance of the first one. So let's say your first isotope was 20%. You would make that into 0.2. So again, this would be the decimal form of percent. Then you will, and again, we're taking the sum of all the different isotopes in the world. So here, plus the mass of the second isotope multiplied its relative abundance. And then you will do this for however many there are. Please note, if we're talking about 100% of that element found in nature, all your relative abundances, since these are decimals, it should equal 1. And if we change those to percent abundances, those should equal 100. And I'll write that right here. So percent abundance of 1 plus percent abundance of 2 plus so on equals 100. All right, so let's try this first problem together. Magnesium exists as 3 isotopes. So you can see off in that chart, I have 3 different isotopes of magnesium, different masses, and their percent abundances. I want you to solve for the average atomic mass. So unlike my equation up here, I only told you 2. You would just have a third one for the third isotope. So here, before I start my equation, I want to zoom in on this chart right here. So here in this problem, they actually gave us essentially 2 different masses. They gave us this 24 and they gave us 23.99. If you're given 2 of them, I want you to use the more exact value. Let's say that this column was not here, you would use this 24. I'm first going to change all the percent abundances to decimals, okay? So here, I'm going to divide by 100. I get 0.7899. Divide by 100, I get 0.1000. Divide by 100, 0.1101. And like I was saying about this part and this part right here, if I took the total of this here of all three relative abundances, it equals 1. And if I take the percent abundances of all three, it equals 100. This is very, very important. All right, so here I'm going to plug in all my information. So here, the first isotope, magnesium 24, I have 23.99 multiplied by 0.7899, plus mass of the second one, 24.99 multiplied by 0.1000, plus the mass of the third one, 25.99 multiplied by 0.1101. And so here, to get my average atomic mass, I get 24.31 AMU. Okay, now one thing to just kind of like dissect and kind of process with this, I want us to remember that we are taking an average of all three numbers. We're taking an average of this, this, and this. So if my highest value is 25.99 and my lowest is 23.99, we want a value that's in between the highest and lowest. If you got an answer of 50, that would not make sense because it's not an average of all three, okay? All right, let's do this one together where I'm going to actually start it for you. And then I'll let you try the rest of it. But this can be kind of a tricky problem, okay? So here, rhenium is one of the rarest elements on Earth. The average atomic mass of rhenium is 186.21. Using the information given in the table, calculate the percent abundance of each naturally occurring rhenium. And so the average atomic mass is, 186.21. So here, they gave us masses, they gave us average, okay? We're solving for percent abundance. So here, let's reference our equation at the top and let's fill in just what we know and kind of dissect it. So I know the average. The first mass is 184.95. I don't know the percent abundance for that, or relative abundance, so I'm going to put X. Plus the mass of the second, 186.96. Y. So here, this is a problem that we're not able to solve for the one variable right this second. So this is actually a system of equations problem. Now, kind of what I did in the top right-hand corner, remember this part right here? I can make a second equation. I know that X plus Y should equal 1, okay? So here, zooming in, if I rearrange my second equation and get X to the other side, Y equals 1 minus X, I can plug in 1 minus X to where Y is, which will change my problem to this. Oops. And now I am able to solve the rest of this problem because now I'm just solving for the variable X. So why don't you pause the video, solve for the percent abundance of our isotope rhenium-185 and rhenium-187. I'll zoom out for the percent, the masses just in case. All right, so let's look at the rest of the problem. So here, your first step was to distribute the 186.96 into the equation. And so here you can see I got that X finally out of the parentheses, and then it became down to like terms. So I boxed the ones that had the X's, so the same variable. So I'm going to add those together, or I guess in a sense you're subtracting. And then I was going to subtract the one value that didn't have an X to the other side, because essentially we're doing an algebraic problem. We're going to try to get x by itself. Eventually, I did get x as 0.3731, and then I can plug that x back into the original y equals 1 minus x to solve for what y is. Please note these aren't the final answers because the question wanted percent abundance, and these values right here are just relative abundances. So times them by 100, I get my 2 percentages for rhenium. Here, 185 rhenium was 37%, and rhenium 187 was 62%. All right. Let's look at this problem right here. So here, determine the average atomic mass of silver. So here to the right is kind of a graph that I was mentioning of what the mass spectrometer would give you if it actually had a sample of silver. So here, I'm noticing I have two silvers, 107 and 109, and they gave us the AMU for them. Now, the issue is what I'm noticing is those percentages are not going to equal 100%. So we cannot go directly to the average atomic mass equation. Our first is going to have to change those percentages to new percentages. So here, I'm going to take the 100% peak, and I'm going to add up the sum of the two, the total intensity. Here, I get 51.84%. Next, I'm going to take my 92.90 divided by the total of those intensity peaks, and I get 48.16%. Next, I'm just going to get this out of the way and divide by 100 to get my relative abundance, 0.5184 and 0.4816. Okay. Next, now I can finally do the plugging everything into my equation. So the mass of the first one is 106.905 AMU. I'm going to use that relative abundance. Then I'm going to add the second mass multiplied by its abundance. So average atomic mass ends up being 107.9 AMU. And so here again, I was hoping for a number that was in between 106.9 and 108.9. So this ended up working great. All right, this is the last problem for these notes. So why don't you pause the video, try this out yourself. This is a you do problem. It's a multiple choice. Yeah. Pause. All right, let's go over the answer. I apologize, that's supposed to say copper, not chlorine. So here there are two stable isotopes of copper, and they have these two masses. So which of the following conclusions about copper atoms can be made from the spectrum below? So answer choice A says copper 37 has the highest percent abundance. Well, this is not true because you can clearly see that 37 has the lowest peak. The melting point of copper is 1085. This is actually a true statement. Were you supposed to know that? No. But here the spectrum would not be able to tell that to us just by looking at it. Copper 35 has the highest percent abundance. I would definitely say it has the highest peak, so this has to be true. But just to confirm that D is not the answer, it does not have an isotope with 18 neutrons. This is actually a true statement. Copper does have an isotope with 18 neutrons because this peak right here, since it's a 35 mass number, 35 minus 17, which 17 is the atomic number of chlorine, is 18 neutrons. So if that answer choice said D, it does have an isotope with 18 neutrons, then that would also be our answer. But here it says it does not. So the statement itself is not true because there is a isotope with 18 neutrons. So C would be our answer.